Welcome back to the series. In this class, we are going to learn the photoelectric effect. It was one of the first experiments that proved that quantum mechanics or new type of physics is necessary to understand the experimental results. It was Hertz much before 1900, that was probably the year of birth of modern physics. It was in 1887. He was doing an experiment in a glass tube. He took a positive terminal and a negative terminal separated by vacuum, and he gave a potential difference, and then he irradiated the anode with X-rays, high energy electromagnetic waves, X-rays. What he observed is he went on changing the frequency of the X-rays, keeping the potential difference between the two terminals at 0. He did not see anything for a long time, and suddenly at some frequency he observed sparks between the two terminals, and he observed a current in the current meter he had in the circuit. And then he further increased the frequency. Nothing happened. There was current in the circuit and it was constant. Then he tried increasing the intensity by decreasing the frequency. He went back to the initial frequency, increased the intensity. How high maybe the intensity was, there was no current. So first thing he observed was that there is a certain frequency, let us call it F0, above which he saw a spark. Then he varied the intensity. He did not see any change below, so no change until F less than F0, and then I for intensity increases, then current, I use small letter I, or that is for current, was also increasing for frequency F greater than or is equal to the same frequency at which he saw the spark. When he reached the same frequency, above the particular frequency, he observed that the current was increasing when the intensity of the radiation was increased. He could not explain why this is happening. And then what he did, he took a frequency, let us say frequency F, which was greater than F0, and then he went on increasing the potential difference, and at certain potential difference he observed suddenly that the current stopped. So for some frequency, I becomes 0. I goes to 0 as V was increased. Okay, so this was another thing that he observed in this experiment. So these were the results of this photoelectric effect, and he did not understand that because the basis of this phenomena lies in the understanding of the material at the microscopic view, which can be done only with quantum hypothesis initially given by Max Planck, but later the photoelectric effect was actually explained by Albert Einstein. As I mentioned earlier, Albert Einstein got the Nobel Prize for explaining this phenomena somewhere in 1905. I think he got the Nobel Prize for his contribution. Let us see what does it mean by this. So initially what happened, was when he was increasing the frequency, you know that metals have atoms, material is made up of atoms, they have arranged structure of atoms inside the material or the molecules, and the electrons are bound to the nuclei. So electrons do not come out of material on their own because there is a force of attraction coming from the nuclei. Just like that in the metals it was that case, and then unless they get sufficient energy which is equal to what is known as the work function of the metal. So here I will write the word work function. Work function. So it is, you can say that the minimum energy required to do the work to bring the electron out from a solid metal. So until you give that much energy equivalent to the binding energy of the electron to the solid, you do not see any electron coming out of the metal. So no electron comes out of the metal. But the instant the energy is equal, and if there is no potential difference between the two, if it is 0, then electrons come out, and some of the electrons might go to the cathode and flow through the wire, completing the circuit. Another thing, even if you increase the intensity such that the frequency is less than the work function, we call that phi, which is hf naught or h nu naught. So that is the energy required for the light to bring the electron out of the material. So that frequency is phi is equal to hf naught. So if the frequency of the radiation is less than f naught, even if you give infinite amount of energy through intensity, it is not going to help, because as per the quantum theory, that is not going to pull the electron out of the metal surface. That is what I have written here. No change as long as intensity is increased below f naught. However, if f is equal to f naught, the critical frequency that observed initially, which is nothing but the hf naught equal to phi, then the intensity was increasing, resulting in increased current. So if you increase the intensity, current will increase. And later what he did was, he kept the intensity constant, he went to f naught, and then he increased the potential, negative potential, which actually opposes the electron reaching this. If this is slightly higher negative potential, then if electron has got 0 energy, it cannot reach there. So then he suddenly observed that there is no current, okay, because this was trying to push the electrons away. It is at the negative potential. So but as we went on increasing the frequency further, he suddenly started observing a current at some point. Okay, so that is what we are going to understand based on the quantum theory of photoelectric effect explained by Albert Einstein with a simple equation: kinetic energy of electrons is equal to the energy of the incident radiation nu minus phi naught, or phi, work function. So this is the energy of the incident light and this is the work function. So as long as this is less than this, the kinetic energy of the electron will be negative, therefore electron would come out of the metal surface. If the energy of the incident radiation becomes more than the work function, then this difference in energy is taken by the electron as the kinetic energy and because of that it will have sufficient energy to reach the other end of the tube to the cathode. So this is the fundamental concept behind this photoelectric effect. Few important points that you should remember related to this is, one is this process was instantaneous. As soon as there was electromagnetic radiation or X-rays, there was a current. This was instantaneous, means it was happening in a time of the order of 10 to the power minus 9 seconds, that is of the order of nanoseconds. And of course, as I have explained you, as long as the frequency of the incident radiation is not going to be equal or more than the work function energy, there won't be any radiation. Intensity has no effect on deciding when the radiation should start. Intensity only changes the current if there is a current. If there is no current, then even if you increase the intensity of the electromagnetic radiation, it is not going to help. And another important aspect we observed is the target metal is very essential. So for different target metals, the work function is different, like cesium, cobalt, nickel, iron, aluminium, gold, silver. They all have different work functions. You can look into their work functions from the Wikipedia or the textbook that you have got. And using this retarding potential, the opposite potential applied, one could calculate the kinetic energy of the electrons. Just a note for you to remember that work function is something similar to the binding energy of an electron to an atom, but it is always less than the binding energy of the electron in an atom. Why it is so can be explained only by the statistical mechanics applied to the solids. For now, you just remember that the work function is less than that of the binding energy of an electron to an atom. So that is it all about. That is the important Einstein's photoelectric equation, and with this we will be solving a couple of problems later. And that's about the photoelectric effect. Let us discuss Compton effect in the following class. Thank you.